Hello students, in this video we are going to learn Eulerian and Hamiltonian graphs and few examples. So before going to the definitions of Eulerian and Hamiltonian graphs, let us first recall what are the walk, trail and path. So we all know that a walk is a sequence of vertices and edges where vertices and edges can be repeated. Also we have seen few examples on this. Trail. It is an open walk in which no edge is repeated, though vertices may be repeated. So the difference between walk and trail is the vertices can be repeated but edges cannot be repeated. Whereas walk, both can be repeated. Then path is a trail in which neither vertices nor edges are repeated. Okay. So we can say that a path is a trail. A path is also a walk. A trail is a walk, but trail is not a path. Right? So now we shall define what is called as the Eulerian graphs. So we define what is called as the Eulerian paths. A path, so you know that a path is a sequence of vertices and edges where no vertex or no edge is repeated. Right? So now, keeping that in mind, we'll define the Eulerian paths. A path in a graph is Eulerian path if every edge of the graph appears as the edge in the path exactly once. Okay. So if you just consider path, it may be a part of the graph, whereas when it comes to the Eulerian path, it covers all the edges. It covers all the edges of the graph exactly once. Next, Eulerian circuit. So here before we defined what are called as the trails and the paths. So a closed trail is a circuit and a closed path is a cycle. Right? Now let us define the Eulerian circuit. An Eulerian circuit is a circuit that uses every edge of the graph exactly once. So what is a circuit? Circuit is a closed trail. That means the starting and the ending vertex are the same. Next, a graph is said to be an Eulerian graph if it has an Eulerian circuit. Right? A graph is said to be an Eulerian graph if it has an Eulerian circuit. So an Eulerian trail is an open trail that contains every edge of the graph G. So the idea of Eulerian circuits first arise from the famous Königsberg bridge problem, which is described as whether one could traverse all the 7 bridges in the town, going over each one of the bridge exactly once and returning to the starting location. And this was demonstrated that it is impossible to do so by Euler, and this gave the birth to graph theory. Now let us consider these examples, say graph 1 and graph 2, figure 1 and figure 2. Let us check whether these are Eulerian graphs or not. So when do you say that it is an Eulerian graph? If a graph contains an Eulerian circuit, then it is called an Eulerian graph. What is an Eulerian circuit? It is a circuit where all the edges of the graph is covered. Okay. Now, if you consider figure 1, it is an Eulerian graph as it has a circuit that traverses through all the edges of the graph G exactly once. There should not be any repetition of edges. For example, if I start from A, I'll start from A, then to B, then C, and then D, then E, again to C, F, and E. So it should be a circuit, means a closed trail, right? Where you can repeat the vertices, but edges should not be repeated. That you should keep in mind. Okay. So hence figure 1 is an Eulerian graph. If you consider figure 2, it is not an Eulerian graph as it has no circuit which covers all the edges of the graph exactly once. Suppose if I start from B, or if I start from A to C, A to C, then A to B, and then to C, again to A, then D, and then C. So we have not covered AB, BC, CA, AD, and DC. But we started from A and we are not reaching A without the repetition of edges. Hence, it is not an Eulerian trail. Now we have theorems on Eulerian graphs. So, which states the first theorem states that if the graph G is an Eulerian graph, then every vertex has even degree. Every vertex has even degree. So it's a very simple proof. If G, the proof is like this: if G is an Eulerian graph, then there is a circuit P in G, right? There should be a circuit in G. This circuit uses every edge exactly once, correct? So you know that in an Eulerian circuit, there won't be any repetition of edge. Then every edge is counted for and is accounted for, and there are no repeated edges. This is clear from Eulerian circuit. Every time a vertex is listed, that accounts for two edges adjacent to that vertex, right? The one before and the one after the vertex in the list. So this shows that every vertex is of degree, even degree, of even degree, and that is the proof. Very simple one. Next, we are going to define what is called as the Hamiltonian cycle. So what is a cycle? Cycle is a closed path. What is a path? Path is the sequence of vertices and edges where there is no repetition of vertex or edge, right? Now, a cycle in a graph G that contains every vertex of G is called a Hamiltonian cycle, right? A cycle in a graph G that contains every vertex of G is called a Hamiltonian cycle. Thus, a Hamiltonian cycle of G is a spanning cycle of graph G. It is a spanning cycle of graph G. What is Hamiltonian graph? A graph that contains a Hamiltonian cycle is called a Hamiltonian graph. So we have a few examples. If you consider cycle Cn for n greater than 3, it is obviously an Hamiltonian graph. Then a complete graph Kn for n greater than or equal to 3 is a Hamiltonian graph. That can also be seen. So consider a cycle of order 4. So this is a C4. It can be seen that we can find a cycle which covers all the vertices of this graph, right? Very simple. When you consider the complete graph of order 5, right? So we have A, B, C, D, E vertices in this graph. So in this complete graph, we have a cycle which involves all the 5 vertices, that is A, B, C, D, E, A. So this is a cycle, right? And hence all the complete graphs are Hamiltonian, all the cycles are Hamiltonian. Now let us define the Hamiltonian path. So a path in a graph G that contains every vertex of G is called a Hamiltonian path in G, right? So it is not a cycle which is a closed path, right? It is an open path. Now we know that a cycle is a closed path. If a graph contains a Hamiltonian cycle, then it should contain a Hamiltonian path. Since cycle is a closed path, if the graph has a Hamiltonian cycle, then it should contain a Hamiltonian path. Whereas a Hamiltonian path can be, and the Hamiltonian path can be produced from the Hamiltonian cycle by just removing any one edge. However, if a graph contains a Hamiltonian path, it need not contain a Hamiltonian cycle. That is clear. Okay. So now let us consider this graph G. Let us check whether this graph G is a Hamiltonian graph or not. So if this graph contains a Hamiltonian cycle, then we say that the graph G is a Hamiltonian graph. What is Hamiltonian cycle again? It is a cycle in which all the vertices of the graph G are covered. So now if I trace the path like this, 1, 2, 3, 4, 5, 6, 15, 14, 13, 12, 11, 10, 9, 18, 19, 20, 16, 17, 7, 8. Right? So 8 and then again 1. So it should include 1 also and 1. So this completes the cycle where all the vertices are covered. You can see, right? Edges need not be covered, but all the vertices should be contained in this cycle, and hence it is a Hamiltonian cycle or Hamiltonian graph. Now there are two important theorems which gives whether a given graph is Hamiltonian or not, condition for Hamiltonian or of a given graph. So let us state this theorem. Let G be a graph of order n greater than or equal to 3. So let G be a graph of order n greater than or equal to 3. So it should contain at least 3 edges, vertices. Then if degree of u plus degree of v is greater than or equal to n for each pair of u comma v of a non-adjacent vertices G, then G is said to be Hamiltonian. So you consider two vertices of the graph u and v which are not adjacent to each other and all such pairs, and find the degree of these non-adjacent vertices. If it exceeds or if it is equal to n, the order, then the graph becomes a Hamiltonian graph. Next, we have another theorem which states that let G be a graph of order n greater than or equal to 3 if degree of v is greater than or equal to n by 2. If degree of each vertex is greater than or equal to n by 2 for every vertex v of G, then G is Hamiltonian. Again, if for both the theorems, the converse need not be true. Okay. Now let us check these two graphs whether they are Eulerian graphs or not, Hamiltonian or not. Okay. So G1 is an Eulerian graph because it has an Eulerian circuit, as all the edges of the circuit are covered. For example, if I traverse from A, B, C, E, D, C, F, G, A. So this is a circuit where all the edges are covered, and hence it is an Eulerian circuit. But it is not a Hamiltonian graph because it does not contain a cycle which covers all the vertices. You don't have such cycle in this. Suppose if I start from A, B, C, D, E, again I should come back to C. So there should not be any vertex repetition here, and hence this is not a Hamiltonian cycle. Now if you consider the graph 2, it is not Eulerian but it is Hamiltonian. Why it is not Eulerian? Because you can see that there are 3 vertices of degree, there are 4 vertices of degree 3. For a graph to be Eulerian, every vertex of the graph should be of even degree. So here E is of degree 3, D is of degree 3, F and B are all degree 3, and therefore this is not an Eulerian graph, whereas it is Hamiltonian, because if I start traversing from F, E, A, B, C, D, F. So this has a cycle where all the vertices are covered, and therefore it is Hamiltonian. Also, we can say that order of G2, that is order of this graph, is 6. There are 6 vertices, and if you consider any non-adjacent pairs, right, it should be greater than, or the degree of those should be greater than or equal to 6. So E and B are non-adjacent. So what will be the degree of E and B? Degree of E plus degree of B is 6, right? Okay, so let us consider few problems. Find the Euler circuit in the graph shown below. So this is the graph which contains V1 to V11 vertices. So now let us see that first you can check the Eulerian, the degree of each vertex. So if the degree of every vertex of this graph are even, then you can easily say that it is an Eulerian circuit. And if you want to find the Eulerian circuit, then you'll have to check the the trail, a closed trail in which all the edges are covered. So since the degree of V1, V3, V5, V7 are 2, V8 are 2, then V9, V2, V4, V6, V7 are 4. The degree of these are 4. And then what about degree of V10? That is also 4. Degree of V11 is also 4. And hence it is an Eulerian graph. Now the Eulerian circuit is, so I'll start from V1, V2, V3, V4, V5, V6, and then I'll go back to V4. You just observe if there is any repetition of edges. Vertex can be repeated. V4 and then V2 and then V11, V6, V7, V11 and V10, V9, V2, V10, V7, V8, then V9, V1. So all the vertices, all the edges are covered, and therefore it is the Eulerian circuit of this graph. Now this is another example. Show that the graph does not contain an Eulerian circuit. You can see that the degree of R and degree of A are 3, which is odd number. Hence we can easily say that it is not Eulerian. Now show that the following graph contains an Eulerian trail. It need not be a closed circuit, closed trail, right? So there is an Eulerian trail. If I start from P, T, which has edge E1, so I'll just include that E1 in the sequence. P, E1, T, E2, S, E3, P, E4, Q, E7, R, E6, S, E5, Q. See, the starting and the ending vertices are not the same. Hence it is an open trail. But it is Eulerian trail because all the edges are covered only once. So next let us consider these examples. Which of the following is Hamiltonian graph? Right? Graph G1, G2, G3, G4, G5 are given. So now G1, if I start G1, so let me just consider the graph G1. So A, B, what is the Hamiltonian graph? It is a cycle in which all the vertices are covered only once, right? A, B, C, D, F. Again I'm coming back to A. Or if I traverse A, B, C, D, E, A, F is left out. So it is not an Hamiltonian graph. Next, G2. G2, A, B, C. To cover E and D, I should come back to B. So this is also not a Hamiltonian graph. Then G3. Let me start from A. A, E, or A, D, C, B, F, G, H, E, and then A. So I started from A and came back to A. So I'll repeat: A, D, C, B, F, G, H, E, A. So this is a cycle, and which covers all the vertices, and hence it is a Hamiltonian graph. Then G4. G4, I'll start from A, B, C, D, E, G, F, A, and therefore it is a Hamiltonian graph. Next, G5. G5, A, B, D, C. Again I am coming back to B. So it is not a Hamiltonian graph. Then G6. A, B, C, D, E, F, G, H, I, and we have an edge connecting A and I, so I can come back to A. So this is a Hamiltonian graph. So this is how we can check the Hamiltonian and the Eulerian graph of a given graph. Thank you.